This is lecture number 11 in our series, The ABCs of Communism. We stopped after a series of lectures on the history of the communist movement and on Marxist-Leninist theory. And then after that, we're going to pick up on each of the Latin American countries one by one, beginning with Mexico, Cuba, Nicaragua, Venezuela, the Guianas, and so forth, until we've covered virtually every country in Latin America as of now. Next year, in the 2016 edition, we will go even further with each one of those, because more or less we're kind of cut that discussion off around 1974 for each of those countries in South America. But what I want to do here today is to introduce you to the archaeological terminology that will be useful to you in understanding our discussions of primitive communism. Because by definition, almost all of this has to do with prehistoric times. So we could also use the term prehistoric communism. But Marx and Engels used the term primitive communism, and so we'll continue to use that. Primitive meaning only primitive technology. These are fully developed Homo sapiens, and there's nothing primitive about them in any biological way. What's primitive is their technological development. Both Marx and Lewis Henry Morgan realized that there was going to be an interregnum between the prehistoric period, about which in Marx's time he had no real knowledge, and in Morgan's time he had to reconstruct what he thought would have happened in prehistoric times based on analyzing the ethnographic literature. Well, it's been a good 100 years since Morgan's writing, more than that really, and of course what we have accumulated in that 100 years is a great deal of actual knowledge about what primitive communist society looked like in terms of its technology, social organization, ideology. That's all been done by archaeology, and the interpretation of the archaeological data is of course largely based upon our understanding of the primitive peoples that have achieved a certain level of social evolution in the historic period. Now, what's the difference between history and prehistory, between historic and prehistoric? Very simple, the invention of writing. Now, there is an interim period in some places, of course, where writing had already been well developed, and these we sometimes call proto-historic, but I don't want to worry about that right now because it's not really relevant for our discussion. The important thing here is, in order to reconstruct what primitive communist societies look like, we have to go to archaeology. Now, we have a vast wealth of archaeological data that's been accumulated in the 20th century and continues to be accumulated now in the 21st century, and we can address many questions about social evolution on a factual basis for that reason. So, when we go next, for example, to Mexico, and then we go to Cuba, and then we go to Nicaragua, we'll be talking about primitive communism based on archaeological reconstructions. And we have a certain set of terminology that you need to use, understand that, because we're going to be using it again and again. Let's begin with the idea of stratigraphy. Now, there's a law in geology and archaeology called the law of superposition. And what that says is that the lowest level in any site is the oldest one. And they get younger as you go to the top, and then the top levels are the most recent. I mean, the bottom levels are the oldest ones. The top levels are the most recent ones. Now, you could say, are there any exceptions to that? Well, yeah, there are. And there's an important point here for some of you to think about. Not right now, I don't want you to cogitate too much about it, but as you get a chance to think about the fact that in the philosophy of science, we like to think that the exceptions should always prove the rule. You'll understand more about what I mean as we go on, but just to take a look at stratigraphy, here we have over here 3 examples of 3 different kinds of stratigraphy. On the top of this page, by the way, all of these pages are taken from my 1976 textbook called Foundations of Archaeology, which was published by a Macmillan subsidiary in Beverly Hills called Glencoe Press. Now, and so you'll see that's the cover of the hardcover edition. About 50,000 of those were printed, I think, originally. And if we get a chance, I'll talk to you a little bit about the history of this book, which is fascinating for a variety of reasons. But at any rate, let's start right here, because here you have natural stratigraphy. You see these layers. What does stratigraphy mean? Well, each of these layers is called a stratum. And each of these stratums are laid down over a period of time by environmental forces, which is why they appear differently. Some will be dark, some will be light, some will have coarse-grained rock or sand in them, some will be very light, and so on. We can reconstruct the environment of deposition, that is, what kind of environment laid down this particular stratum, and we'll get to that also. But here you can see a natural stratigraphy in the sidewall of a pit, let's say 5 feet deep. Commonly in the U.S. we used to dig in 5 by 5 foot pits. When I went to school, we were already using the metric system, so these would be 2 by 2 meter pits, but the principle is the same. Now, if you look below that, and this particular one right here, you'll see that we have cultural stratigraphy. We have certain artifacts in one layer, then there's a layer with nothing in it, then another layer with more artifacts in it, another layer with nothing in it, and so on. So here we have a cultural sequence of cultural stratigraphy. These are the oldest ones, and these are the most recent ones. Now, what do you do when you want to have stratigraphic control and you don't have any natural stratigraphy and no known cultural stratigraphy, and you haven't found any in your test pits? Well, in that case, what you want to do is you might dig in 5 or 10 centimeter levels. And over here, in this, you'll see blank here, but over on the right side, you'll see that we have a bunch of 10 centimeter or 5 centimeter levels, whatever you happen to be digging in. And so we would bag up stuff that we find, flakes and blades, and I'll discuss that terminology in a minute. Stone flakes, stone blades, any other kind of thing that we think might have cultural significance, that is something made by man or human. And then we'd label it level 1, level 2, level 3, and so on, and then the actual depths of it. Okay, so if an exception to this might be, for example, let's say that you have this natural stratigraphy here, and you dig a site, and it's upside down. Well, how could that happen? Well, this is the exception to the rule, that the oldest is on the bottom and the youngest is on the top. And the exception proves the rule, and that is, if you were to, for example, have a glacier pushing on top of, pushing this land forward, that glacier might easily turn that entire sequence upside down, mightn't it? Things like this happen, and then we encounter them in the field, and we say, well, this should be on the bottom. Well, that in itself tells us that, well, something turned that sequence upside down. That's what I mean by the exception proving the rule. And of course, that would be the same for any of these others for that matter. So here are 3 different ways in which we talk about stratigraphic levels. Now, when we get to dating here in a minute, and I'll mention it right now because we're looking at it, until the post-World War II period, we didn't have real absolute dating means, except, well, a few exceptions, such as tree ring dating, we'll talk about in a minute. What we had to do, therefore, was we could say this particular site, level up here, if we call these 3 cultural levels A, B, and C, we could say, well, B is post-A in time and pre-C in time. That gives us a relative period of time. If we want to make that into an absolute dating, we would have to tack in an absolute date at some point. And with the invention of radiocarbon and radiometric dating in general, we were able to start putting absolute dates on relative sequences. So a relative date is something like this. We know it's older than something and we know it's younger than something else. An absolute date is if we put this date right here at 5,250 years ago, according to radiocarbon, is after a date down here, and it's before a date up here. So we're beginning to put hard dates in contemporary years onto levels within the ground, and radiocarbon dating has become so common in the years that I've been in archaeology that we have been able to rely very heavily upon that. But there's never a point at which we don't, first of all, establish a relative sequence. If for no other reason, then we're going to have to take some charcoal or some kind of material that's going to be dated by carbon out of there and send it to a lab, and that's going to take a while. In the meantime, we have a relative sequence of dates, and pretty quick we're going to put some hard dates on it. As a matter of interest, I think I mentioned when we were talking about Mexico, or when we're going to talk about Mexico, the first radiocarbon dates ever were produced by my mentor, Richard S. McNeish, based upon a corn cob that was excavated in the Tamaulipas region of Mexico. And he sent to Dr. Libby in Chicago. Now, at that time, 1948, there was a real concern among the men that had built the atomic bomb and that were building the hydrogen bomb about the kind of work that they're engaged in. And they wanted to put their atomic science research to some kind of use other than building bombs. So they were happy to try this new dating technique. And I'll explain to you how radiocarbon works later on as we get into it. But at any rate, McNeish got the very first carbon date ever done anywhere on that little corn cob, and it came around 4,500 years ago, as I recall. Okay, so that put us in an entirely new, it gave us a tremendous advantage, because what McNeish was looking for, he and his associates, was the origin of agriculture. Well, we already knew that the first corn in the New World was not corn that you and I would recognize at all. It was a one little grass seed on top of a long blade of grass called teosinte. Now, that was a long time before this primitive corn cob, yes, of 4,500 years old, but a long time after the original teosinte, probably at least 5,000, maybe 10,000 years after the original grass seed process of domestication had begun. That is, humans would have begun selecting certain grass seeds to preserve and plant, and that over many generations they would have started to produce what is called zea maize, or what you and I call corn. Okay, enough comments on the back of that. Now, we're going to skip here real quick to show what a community pattern looks like in an archaeological site. What we have here are 4 different examples on, if you want to get this book, you can still get copies of it from used bookstores on page 114. And I think we're going to bring a second edition of this out in ebook form sometime in the future. But at any rate, this, what you're going to take a look at right here, we have 4 examples of ways in which a pattern of community layout, that is houses and fire pits, places where people cooked, places where they lived. There are 4 different examples of how that works right there. You can reconstruct a pattern of way a community is organized by the careful excavation of layer after layer until these features are exposed. Now, an archaeological feature, as opposed to an artifact, is any tool that was, or not necessarily a tool, anything that's created, could be a ceremonial object, something that's created by men. But also created by men are the features that are left in the ground, and by women too, of course. Now, so we have artifacts and features that are being mapped layer by layer. Now, in my day, we did all of this without the use of modern equipment. We didn't have GPS, we didn't have lasers, all that sort of thing. What we had to do was to shoot in an elevation someplace, put with a regular transit, the optical transit type, put a stake in the ground, and then take a string around the base of that stake, stretch it out over the site, put a carpenter's line level on that string so you were sure it was at the level, then take a tape measure and measure from that string down to wherever, say you've got an arrow point sitting down there on the bottom, or a fireplace. You'd measure all that in, you'd measure the distance down here. The idea would be that at some point in the future when you get back to the lab, you will map all of this stuff in. Now, sometimes that happened, just as often it did not. These notes would get stuck in somebody's drawer and they'd stay there for decades. everything's changed in that regard. Now you can plug it all into a computer at the site, and you can get an on-the-spot three-dimensional printout of what that site looks like all the way across every place you've taken a measure. And this is a tremendous advantage of technology, which we did not have available to us when I was in school, and when I was teaching archaeology, for that matter, or when I was doing it. But now that's the way you would learn if you were doing it. So we can map out these places where the houses are, where the fireplaces are. From a practical example, I'll tell you that when my expedition was along the Taltan and Stikine rivers back in 1969, 1970, the Stikine River drainage is in the far northern part of northern Columbia, British Columbia, close to the Yukon border. We found an area which, when you went down just a few centimeters, you would see that you had a house pattern, a fireplace in front of it, and then next to it another house, a fireplace next to that, and so forth. Now, that was a village layout, and that told us quite a bit about what we have there. From the ethnographic record of what we knew about the Taltan Indians, and we were able to show that this whole village was broken up into what are called ethnologically, they're called phratries, moieties, and clans. We don't need to worry about this technology yet, but you can begin to see archaeology is therefore capable of reconstructing exactly what these community patterns were looking like. We'll come back to all of this in another lecture, but I want to get you started so that we can get into the lectures on primitive communism. Now, in addition to that, we have settlement patterns. In other words, that whole village site is just one of many other village sites which would be occupied by these people at different times of the year. During the winter they might be in one area, during the summer they might be in another area, and so we were able to, here's what, when you do this across the entire region that you're studying, you can begin to see how these people move from season to season. And so this is what we call a settlement pattern. Now, here we have a settlement pattern of Paleo-Indian times, that is in New Mexico, where at certain times of the year you have people that are hunting big game. Other times of the year they are getting together for communities, sites, and activities, and we can map that out also. And so that's another example of the way in which we can use settlement patterns. Each individual site is usually uncovered initially in a site survey. Well, what is that? This is a form used back in my day by UCLA site survey people, and what they were doing, what you would do is fill out one of these. Every place you have a team of people walking along a given area that you have decided that they should examine, and they're looking for evidence, cultural evidence along the way, artifacts or features. When they find a place like that, they'll designate it as a site, fill out one of these forms. And that's usually as far as they go. The next step would be to put a test pit in each one of these so you can begin to get a vertical control like the ones we had when we started this lecture, and we were talking about stratigraphy. So it's not all that important. I mean, you could have all kinds of different site survey forms, but that's one we used to have available to us. Now, you remember I said that these, back in the old days, what we used to do was just shoot in we'd shoot in a line with a transit over a site, and then we would eventually map that site out into 2x2 meter or 5x5 foot squares, and this is an example of how that would have been done at that time. And it also shows you that you can see here there's some pots and other things that are buried in the natural stratigraphy, creating some cultural stratigraphy. We have to take a line level with a carpenter's level on it, a line with a carpenter's level on it, and then measure down to each one of these, and we get the depths. the computers allow us to plug that in immediately on site, and by the time you're done for the day, you should produce every day, just the way you would produce rushes if you were making a movie, every day for your people to take a look at, your directors, producers, and so on. Well, here we could do the same thing now. Every member of the expedition can see at the end of the day, well, this is what we found so far. This is what this site looks like so far. We have pottery over here, which is associated with the kitchen area in an individual house. As a matter of interest, I remember in Chico, California, when I was on my first archaeological field school, I accidentally came down on top of a Maidu woman's kitchen, and her house had burned down right on top of it, and everything was in place. I mean, it was as your kitchen here would burn down, and then the fire department would come in and they'd say, well, all of your utensils are still in their drawers. So we came right down on top of that, and to me at the time was a very exciting thing. Of course, you get a little jaded about getting excited about finding things after you've done it for a few years, but at any rate, there we go. Now, here's this site up in northern British Columbia that was a principal site that I wrote my doctoral dissertation on. What we found here was pretty clear-cut evidence for a migration of people out of Northeast Asia into Northwest America in the first few centimeters that we excavated. Now that shows you why it's very important to be careful when you're excavating, because if you just came in there with a shovel and dug all this stuff up, all the information would be lost. What you do is come in here with a trowel and a toothpick and other dental picks and paint brushes and work away at what turned out to be cultural stratigraphy. As soon as I realized we had microblades in here, that yes, we want to keep using arbitrary levels, bagging it the first 5 centimeters, the second 5 centimeters, clear across the whole site. But when we soon found out that all of the microblades were in one place, we began to see cultural stratigraphy. What wasn't immediately apparent to me at that time, but we realized within a few weeks of returning to Calgary, that all of these obsidian microblades and the microblade cores that we have been excavated were absolutely identical to what had been excavated by a man named Kobayashi in Hokkaido Island in northern Japan. If I remember correctly, it was another graduate student named Knut Fladmark who showed that to me. Well, as soon as that happened, it's like one of those things where click, 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 everything comes together in your mind, and I realized all of a sudden what a stupendous discovery we had made. But we had made it originally by accident, and the reason that it was a good discovery is because we had absolute depth control, very careful excavation over the entire process. If we could see this down here, you would see this is another site dug in a somewhat different way by Richard S. McNeish in Mexico. I'm not going to go into that yet, but I want to give you a general idea. So what we would say, for example, is we have a microblade component in ice at this ice mountainside along the Stikine River at site so-and-so. We go 5 miles along and we get another microblade component on the Stikine River, and so on and so forth. So a component is, as you're beginning to see, a local manifestation of a certain phase. We're going to talk about horizons, phases, and components in a minute, but you're beginning to see how that terminology comes together. Okay. Now, what do we got here? Well, what this is showing you is what I've been describing to you in words. We have a line level out here with a carpenter's line level on it. You measure down to this feature, which you have found in a site. Measure the feature itself and then the depth below that level. And then, using a trowel, not that it matters, but generally they like to use Marshalltown brand trowels. It kind of does matter in a way because the others tend to fall apart fairly quickly when they're used in the ground constantly like this. Anyway, you can see how this trowel is cutting away first of all, the grass and the roots above there. And then he's got some natural stratigraphy he's trying to follow right there, taking away that level only. And then there's another level below that. Again, so you can see how the trowel is being used here. Just as often we might use, especially in test pits, a flat shovel that's been filed down so it has a sharp edge, and then you try and take 1 centimeter at a time off of a 2 by 2 meter square area. Bag that whole thing up. So that's another way of doing it. You wouldn't have to use it with the trowel. You could try. The advantage, of course, is that you can go faster if you have the shovel, and you can cover more territory more quickly. And if you're good at it, and there are people that are just as good with shovels as they are with trowels, then you're in good shape. Now, everything that you bag up or that you find individually, you want to put a label on. So this is an example of what a label looks like. And then you would paint, I'm going to show you in a minute, you would paint that number onto the artifact itself. Now here's one that's actually taken from that particular expedition. It says Ice Mountain Archaeological Expedition Field Catalog Form. You can see there's a number, a location, and some other data and remarks over here. And the date, this one says June 4th, 1969. So that was the date. That's when we were up there doing that particular site. Well, that's before a lot of you were born. Not that that's important. But at any rate, now, the artifact itself. Let's say you're down in the Southwest or in Mexico someplace and you've got pottery. Well, let's say here's a piece of pottery. What you would do here is to put a silver or white fingernail polish right there. Then you would come in with a pen and black ink and then write a number which would be, for might correspond to one of these numbers on this particular form. See if I can't keep that finger. So you put down the number that goes to the catalog, and then you cover it with clear nail polish. And this could turn, if you have thousands of pieces of pottery, this could turn into a big project, and so you're going to need quite a bit of help here. In the old days, or in my day, you used to have plenty of students that would be glad to come in and do it. Over the years, I've learned that it's been a good idea to organize an amateur archaeological society in various states and provinces of the U.S. and Canada, where people that are looking for a way of making some kind of contribution and having a constructive hobby in life can come in and give professional archaeologists a real big hand, because a lot of this work is very time consuming, and if you have to pay somebody to do this, it's going to cost you a lot more than we usually have. Archaeology started out as a activity by the very wealthy people in Europe and, who had nothing else to do and had plenty of money and plenty of slaves and serfs to produce money for them. And it was a dilettante's hobby sort of thing. Of course, as time went on, it became a professional activity, and people had to start paying for the kind of labor that would be required to do this. It became an expensive project, and if you weren't willing to wait around for 10 or 20 years to get a grant to pay people to do things, which I never was, then your best bet is to recruit a bunch of amateurs and give them a chance to make a real contribution in archaeology. So that's what I would recommend to any of you that are thinking about it. Don't let money stop you, because there's plenty of people who will pay you money to go on an expedition. I've never had people pay me money to do that, but I know that there are other archaeologists who every summer when they're not teaching, they go on, they get paid to go teach a bunch of people who pay the company to take them on a tour someplace and dig an archaeological site. So at any rate, let's go back to our relative dating discussion here real quickly. What we have here in this particular example is a stratigraphic set of a stratigraphic sequence based on natural stratigraphy, cultural stratigraphy, and you can see the dates have been plugged in here. Now these are radiocarbon dates, and they've been plugged in this is just an example, but what it does is show that the oldest strata is on the bottom, the youngest is on the top, but it shows you a lot more than that. It shows you how much time it took to get from each point to the next. So we're beginning to get real time control over social evolution in the ground. And as time has gone on, this has gotten to be better and better and better. Okay, now, there is another way of relative dating, which is very important. Started in Egypt by William Flinders Petrie back around the turn of the 1800s of the 1900s. And what he did was to show in Egypt, what I'm trying to do here in general, is to show that you can have a series of changes in an artifact type. So let's say that this is an idealized sequence, it's not a real one, but let's say that what we have here, we have determined that this is a continuous sequence in the evolution of a certain type of arrow point. And it starts here, it changes to this form, and this, through time, it's beginning to change these forms. Now, if you find this same sequence in other sites, but let's say in another site next to it, it starts here. But you notice that you have these stages right after it in the other site. So that allows you to place that site over here. And then you find another site maybe miles away, and it has just these three down here. So, but in that sequence, so you say, well, this site isn't earlier than these other two, we put it over there. This is called seriation, and it's extremely useful in many ways. Now let me show you how that's could be used, how it has been used in Mexico by McNeish and his associates. When each one of these is a pottery type of a certain series, but you can see that some of them are grouped right in here, others are right in there, right in here. So let's say you go along and find another site, and in the other site, all you have are these artifacts, but they're in that percentage all the way up. So you say, well, this other site belongs here in time, which he calls the Venta Salada phase. This is from the Tehuacan Valley in Mexico. And then you come to another site, and you say it has just this stuff. So you say, well, that's what this is from the early, early Santa Maria phase, and so on. So seriation puts you there. Now all you got to do in any of these sites is plug in a radiocarbon date, and now we're turning the whole thing into an absolute sequence of dates, and you begin to. So in Tehuacan we have about 10,000 years of history in this sequence. Okay. Now what I want to do is put up tree rings. Tree rings are an absolute dating method because all you have to do is put an absolute calendar year on one end of it. And then every time you cut the tree in half, and then you measure the cambrium layers that are laid down every year until you have a sequence that allows you to say, well, this log, let's say we're in New Mexico or Arizona, you've taken a log out of the ceiling of a archaeological site you've excavated that has a pueblo in it. You took a log out of that pueblo ceiling, you cut it in half, and you find that the tree ring sequence for that log fits perfectly in this established. So now you know how old it is, and you know exactly what year it is. So that's another thing. Now, let's go to radiocarbon dating real quick. What we have here, the reason that this, now actually the way in which we count the number of carbon atoms of whatever isotope has changed quite a bit in the 50 years I've been in archaeology, but I'm not going to worry about how that's counted, except to tell you that right now we can count every single carbon atom, 12, 13, 14, in a sample. Every single one. But that's not how we started out that way. But the point is this. The Earth has a heavy nitrogen concentration in its atmosphere, which is under constant bombardment from cosmic rays, which are high-speed protons. Now, most of this comes from the sun, but not all of it. This is not sunlight. Sunlight is only photons. There's nothing else in sunlight but photons. But in addition to that, at lower velocities are constantly being kicked out other subatomic particles. Some of these are big and heavy and come at high energies and are called cosmic rays. Now, those will strike the nuclei at a certain percentage of this. When you have enough hydrogen in the atmosphere, as we have in the Earth, for example, then they will eventually start striking nitrogen nuclei. And when that happens, they spin off different isotopes of carbon. Now, you'll remember that the only difference between any element and any other element is the number of protons in its nucleus. The difference between isotopes is that carbon-12, for example, has 12 protons in its nucleus and 12 neutrons. Carbon-13 is carbon because it has 12 protons, but it has 7 neutrons, so it's heavier, and it's called carbon-13. Carbon-14 is carbon because it has 6 protons, but it also has 8 neutrons, so we have carbon-14. These are all created at different ratios in the upper atmosphere. However, chemically, all elements behave the same, regardless of their nuclear structure. That is, they all have the same number of electrons, so chemically they behave the same way. What does that mean? Well, it means that plants, which absorb carbon dioxide and give off oxygen, are taking it in. They don't care whether it's carbon-12, carbon-13, carbon-14. They're taking it all in at a certain ratio. And that will, now, let's say years go by. You dig up that plant, or the animal that ate that plant, and now you evaporate, or you count the number of carbon atoms of each isotope that are present. And that will tell you how old it is, because we know that the disintegration rate for these of these carbon atoms is 5,730 years, if I remember correctly. And if we have only of carbon-14, which is unstable, carbon-13, carbon-12 are stable. Now, carbon-14 is what we're looking for because it's one of those isotopes created on a regular basis by cosmic ray bombardment of the upper atmosphere, and it disintegrates at the rate of, if I have 1 gram of that stuff right now, in 5,730 years, I'll have half a gram of it. It will have disintegrated into other elements. So when we're digging up, say, charcoal from a fireplace, or bones, or something that's got a carbon content in it, we get let's say we get a ratio that says, well, there's only half as much carbon-14 here as there would be if it had been created today. We say, well, then it's 5,730 years old. That's what half-life means. You hear the term half-life a lot. If a person, usually you hear it in the context of, well, if that bomb goes off, it's going to be, that half-life is going to be about 5,000 years before we can ever come back to that part. Yeah, well, that's true. But at any rate, that's a military application. So that's how radiocarbon works. Now, there are many elements which disintegrate at a known rate. Potassium, argon, for example. Potassium will disintegrate into argon, and if I remember correctly, its half-life is about 1.2 billion years. So that's of course not useful for us in archaeology, because we're only looking at a few thousand, or a few 100,000, or at the most a few million years in archaeological sites. But if you were a geologist and you were looking at the earliest rocks in the world and that sort of thing, then you would find that if you found that you have a half-life of 1.2 billion years in a rock for based upon the amount of argon that's present, then you would know you have a pretty old rock. It goes back to the time of, well before the emergence of complex life on the Earth. But at any rate, there's another thing so there are many elements besides these two which are useful for dating for geological purposes, if not so much for archaeological purposes. But the point is the same. Now, there is such a thing as fission track dating, and this is a photomicrograph, what I used to call microphotographs before I knew any better, of the tracks left by a splitting uranium-238 atom. And this is reprinted from Techniques for the Archaeologist by Henry Michaels and Elizabeth Ralph, published by MIT Press. And what happens here is you have a U-238 atom which is splitting at a normal rate, and at that normal rate of fission, and it's creating a track in a rock that will preserve it. Now you cut that rock with a rock saw, polish it up, and what do you have? Well, one of the things you have, then you'll be able to see whether you have any fission tracks in there from U-238, and we know the rate at which that happens. I want to talk to you also about obsidian hydration dating, if I can find it. Okay, let's take this one here. Now, we use this a lot in my microblade research up in northern British Columbia, Canadian subarctic, because we were working next to a volcano called Mount Edziza on the map, the Indians called Ice Mountain, that produced, because it was Canada's only active volcano in that area, it produced quite a bit of obsidian. Obsidian is a glass, and that has cooled so quickly after the lava has been ejected into the atmosphere, or under a lake, or wherever, that it congeals as a glass. Now, one of the things, this is a dating technique which had just been developed, and I had a colleague named Leslie B. Davis, who was another graduate student at the time I was up there, which was 68, 69, 70. He was doing his research on obsidian hydration. He was using a lab at Pennsylvania State University to do the actual sectioning. And now what's the point to all of this? The point is this: if you can control the temperature in a particular area, which is obviously easier to do in the far north or at the equator than it is in the temperate areas where you have a lot of temperature variation over, say, a period of 10,000 years, it's not going to change that much in the north or at the equator as far as the chemical activity ratio is concerned. So if you can control the temperature in an area, then the rate by which the outer surface of a piece of obsidian that was knocked off, say, 10,000 years ago, up until that time, there was another surface on that piece of obsidian, but some Indians picked up a rock, a nodule of obsidian, knocked off whatever was on the outside, and started to make an arrowhead out of it, or a spear point, or some such thing, a microblade. Then you can you can section that, look under the microscope, and you can see this line right here. Now this is the line that has been altered by the exposure to the atmosphere. And that happens at a controllable chemical rate. If you can control the temperature, you can calculate the age of that individual artifact pretty precisely. The results for us were excellent because they concurred with everything else that we could put together, and they were our earliest obsidian hydration dates, that's what the name of the technique is, were 9,500 years ago, and so we were pretty happy with the application of that technique there. Now, there's such a thing as called magnetic dating. Now, paleomagnetism is something we can reconstruct. We know this: the North Magnetic Pole is constantly moving. There's a difference between the physical pole and the magnetic pole. The physical pole you can just see when if you have a globe and it's going to be at an angle, that's the physical pole. The magnetic pole depends upon what's happening at the source of magnetism, which is in the core of the Earth. And things are happening there which are not fully understood at that time, or even now for that matter. And what the consequence is that the magnetic pole goes all over the place. So, since we know that, and we know the pattern for different periods of time of the movement of that pole, if you can get a a sample of something that had been boiled off, let's say a rock in a fireplace, a piece of pottery or whatever, and boiled off all of the electrons when it was being fired, and then if it has not been fired again since then, you might be able to determine a pattern of orientation of the magnetic lines of force. And if you could match that up with this, then you would also know what the date is, because this pole is constantly moving. So that's what's called paleomagnetism. Now, there's a cultural kind of dating that we use all the time, also in areas where you have high cultural development, such as China, Iraq, Egypt, Mexico, and Peru, based on calendars. And in this case, these people left us a written record of the date based upon their calendrical system. So if you have a calendar in a society, such as Mexico had with the Mayans or the Aztecs, then you should be able to, you can read on there. Now, as we go on in this lecture series, we make about, well, we know that this particular series, set of dates in Mexico goes to a certain date because we found it on a stele. Well, of course it didn't say, it doesn't say 733 BC on that stele because they're not using our kind of calendar. But it has a calendar which is just as accurate as that one. What we have to do is figure out how they're doing it. And so there's a certain area of archaeology which is devoted to calendrics. But in all these high cultural areas we have calendrics, and we can therefore put Christian years on top of whatever the local native years happen to be. All right, this is enough to get us started, but I want to go back over a couple of other things. So when I talk to you about Chile, for example, in the very early sites there, I'll say that there's a component of this phase close to the ocean, and another one some miles away inland, another component of the same phase, and then above that, another component of a new phase. Well, these phases in each of these sites, the archaeologists that dig them usually name them, and they should have a decent phase should have more than one component. In other words, it should manifest itself in more than one place. Now, let's say that you have a Chavin horizon. What does that mean? Well, let's say you have a whole bunch of Chavin phases with a whole bunch of Chavin components, and it extends over all of northern Peru and all of adjacent parts of South America. We would call it horizon. Okay, so those are terms that we're going to be using here pretty quick, because when we talk about primitive communism in the New World, we are talking about specific archaeological data which have been used to reconstruct what the first societies look like. All societies, everywhere in the world, started out as communist societies. And so this is the longest period of time that humanity has ever existed in any socio-cultural stage. And one of the nicest things we have going for us in our study of the fight for communism in contemporary South America or Latin America is we have the ability to reconstruct what happened in every country from Mexico to Argentina to Chile and Brazil, Venezuela, and so on, from the very earliest times that humans occupied them, because by definition the very earliest humans that came there were primitive communists. In place, they eventually evolved into tribal agriculturalists from hunters and gatherers, but tribal agriculture is also primitive communism. In place, mankind left primitive communism and moved into what we call civilization, or what might more accurately be called slavery. The transitional period between this primitive communism, whether it's hunting and gathering or tribal agriculture, is a period of chiefdoms. Now, it was Karl Marx who discovered that the transition from pre-class to class society occurred in this chiefdom period. But it was the last thing he discovered in his life. In the last 7 years of his life, and he died in 1883, he spent 7 years studying the research of then contemporary anthropologists, especially Lewis Henry Morgan, but we know he was familiar with all of them. How do we know that? Because we have his original handwritten notes and they are now published as, what is it? They were published in 1972 by a man named Lawrence Crater, and I think the title in the libraries is the Ethnological Notebooks of Karl Marx. So, if you try to look for this under Crater, you're not going to find it. You've got to look under Karl Marx, and then the Ethnological Notebooks. And the 72 edition is in most libraries. Now, when you get that, this man wrote a 72-page introduction to this 1972 edition, and I have no disagreements with it. I think it's well worth reading. But the important point, you don't have to read all of that to see that what Marx discovered was that the transition from classless to class society, based upon a reconstruction of what must have happened in prehistory, based upon his ability to understand the ethnology, the anthropology, the anthropological record of his time, that is the late 1800s, done by Lewis Henry Morgan, Tyler, Maine, and the rest of the early anthropologists, was that it's in the differentiation of society into classes begins in the process of ranking division during the chiefdoms, simple chiefdoms, and then what I call advanced theocratic chiefdoms. So here we have in the New World an opportunity to see this entire process from the first arrival of people in the New World, who by definition were primitive communists, and then, depending on when they got there, you have thousands or tens of thousands of years from hunting and gathering to tribal agriculture. Then the invention of agriculture propels them into a system of stages of chiefdoms, which we discussed in the earlier lectures. The most advanced group of these chiefdoms have begun to differentiate into social ranks. And given enough time, some of these ranks will get title deed to property, and they will completely separate themselves as classes. And if they can get armed force in their own hands, armed force is the state, the army and the police, then that combined with their ability to control ideology through the priests, who have ruled as theocrats in advanced theocratic chiefdoms until now we have military dictators, policemen or cops or soldiers who have become the bosses because they've got the clubs and the swords, and in time they'll have other more sophisticated weapons, but they can control a mass of people and do all the work by force. So we have therefore the division of society into classes. We see this clearly in every part of the New World because we have such good archaeological control, far better than we have in the Old World where archaeology actually started. So that's changing somewhat because the Chinese have picked up on McNeish's methodology, and the archaeological reports coming from China are detailed, excellent, and increasingly numerous. Unfortunately, the wars over oil in Iraq, which was the next major source origin of civilization or origin of slavery, will prevent us from doing any research there for the foreseeable future. And Egypt's not a much safer place to be either right now for obvious reasons. So I don't anticipate much coming out of that part of the world, but China will lead the Old World in terms of the reconstruction of these phases. And we already have all the data we need from the New World to produce the kind of lecture series that you're getting right here. So given that, I think I'm going to stop for today, and then we'll decide where we're going to pick it up on the next lecture.